Next, we're going to see how we can find the maximum or minimum value of certain functions. So we already saw some of that with the extreme value theorem, and some of the examples we do, like this one, will be direct applications of the extreme value theorem. But some, well, remember, the extreme value theorem requires a closed and bounded interval, so an A to B closed. And for some applications, like this one, we're going to be able to find such an interval, and then we can find the absolute maximum, absolute minimum of the function on that interval. Sometimes we're not going to have a closed interval necessarily, and in those situations we're going to have to consider a slightly different argument. But for some, we will directly apply the extreme value theorem. So here, let's look at this example. We're going to do, I think, 6 examples. A farmer has 2,400 feet of fencing and wants to enclose a rectangular field that borders a straight river which requires no fencing. So a rectangular field borders a straight river. There's no fencing on that one side against the river. And the question is, what dimensions maximize the area, and what is the maximum area? So in all of these, the first observation I like to make is, what are we doing calculus on? Meaning, what are we trying to maximize or minimize? Here, it says what is the maximum area. So we're going to try to maximize an area function. The area of what? Well, we have to draw a picture here. 2,400 feet fencing wants to enclose a rectangular field that borders a straight river. So here's the river. Rectangular field borders the straight river. And we want to maximize the area of this field. Well, it's rectangular, so let's label the sides. So we want to maximize the area of this. Area equals xy. And with calculus, we can maximize things. But notice here, the area function is a function of 2 variables, x and y. We want this to be of 1 variable, because that's all the calculus we know. Well, other information in this question can be used to eliminate a variable. It also says we have 2,400 feet of fencing. So x plus y plus x must be 2,400. We want to maximize area, I'll say. Here's our area function, but we also have a constraint on our x and y. 2x plus y equals 2,400. Now, with this constraint, we can find a closed interval on which our x and y, I like working with x, because I'm used to working with x in calculus, but with this, we can find a closed interval that defines our possible x values. Do I want to do that first, or do I want to do the other thing first? Well, let's keep that in mind. I'm going to do the other thing first. We have these 2 functions. Our second is our constraint function. So we can solve this one for x or y and eliminate x or y. Here I'm going to solve it for y. So I'll say, so y equals 2,400 minus 2x. And so our area function, since we solved that for y, we can now write our area function in terms of just x by replacing y with 2,400 minus 2x. Area is x times 2,400 minus 2x. And I'm just going to distribute that x. 2,400x minus 2x squared. Now, we have a function. To directly apply the extreme value theorem, we would like to find a closed and bounded interval of x values. Now, not all x values work here, because we have this constraint. X equals 1,000,000, for example, won't work, because x and y are always going to be positive values. But what is the largest, well, let's say, how do I want to say it? It's probably easiest to see with this y equation, our constraints on x. So this y value from this y equals 24 minus 2x, the largest that can be is 2400. The smallest it can be is 0. The largest is 2400. When does that happen? That happens when x equals 0. And what is the smallest that can be? Well, the smallest y can be is 0, which happens when x is 1200. So that gives us our interval 0 to 1200. So I'll write that here, on 0 to 1200. So right now, we're looking to maximize a function on a closed interval, 0 to 1200. Well, we can do that by finding the critical points and the endpoints and evaluating our area, and then we want the maximum, so picking out the area. Now notice, before doing any computations, the area evaluated at 0 and 1200 is going to be 0, because it would be, in one case, an infinitely narrow rectangle in this way. In the other case, if y is 0, infinitely narrow in that way. So it wouldn't be a rectangular field, it would be a linear field. But we'll get there. So here, how do we do this? Well, we need the critical points. So we need the derivative of a, where it's 0, where it's undefined. It's never undefined. The derivative of a is 2400 minus 4x, never undefined. When is this 0? Well, it's 0 when x equals 600. So now, let's compare the area at our critical points and our endpoints. So area evaluated at x equals 0. Notice down here, area is a function of x, and only x down here. Area at 0, well, if x equals 0, the area is 0. Area at 600, area at 600 is something. Area at 1200 is also 0, because y would be 0. What's the area at 600? Well, what do you get? You get 600 times 2400 minus 1200. So 600 times 1200. So 720,000. So right here, we go back and make sure we answer the question, what dimensions maximize the area? What is the maximum area? So x equals 600. This is our largest number, so this gives the maximum area. So x equals 600, and y equals, we want the dimensions, we need the x and the y. If x is 600, then y is 1200. You could get that from the diagram or from that this equation or that equation. So x is 600, y equals 1200, they're both feet. Give a maximum area of 720,000 square feet. So in this example, we were able to find a closed interval based on the information that we have. Let's look at another where that is the case, and then we'll look at a couple where that isn't the case. There is more than one way to do this. So next, let's look at this example. The sum of two numbers greater than or equal to 0 is 16. Minimize the sum of their squares. Well, again, the first thing I like to do is observe the function we're doing calculus on. Here, minimize the sum of their squares. Well, we have two numbers, let's call them x and y, and we want to minimize the sum of their squares. We're going to do calculus on that function. So I'm going to call it something, I'm going to call it capital S for sum. We're doing calculus on the sum of the squares, x squared plus y squared. Now, we also have other information in this which will allow us to turn this into a function of one variable instead of two, because it says the sum is 16. The sum of the two numbers greater than or equal to 0 is 16. So x plus y equals 16. But with this information, we can find a closed interval that defines our x and y values. It says the numbers are greater than or equal to 0. I'm debating if I want to do that now or later. I like it in the first one. Well, let's solve for y and then find our closed interval. So we have this constraint equation. We can use this to eliminate y. So y equals 16 minus x. And then s equals x squared plus 16 minus x all squared, since y equals 16 minus x. And I'm just going to simplify that. (16 squared is 256). So we have our function, but can we find a closed interval defining our x values? Well, we can. We know x and y are both greater than or equal to 0. But we also know that y is 16 minus x. We know x plus y is 16. So with those, x can't be, for example, 17, because then y would equal -1. The largest y can be is 16, so the smallest x can be is 0. The smallest y can be is 0, so the largest x can be is 16. So we have our function that we're trying to, in this case, minimize on the interval 0 to 16. Well, let's do our calculus. We know the minimum is going to occur at a critical point or an endpoint. So derivative is what? 4x minus 32. We want to set that equal to 0. That's 0 when x equals 8. So now we need to compare the sum evaluated at the endpoints and the critical points. So at 0, at 8, and at 16. The sum at 0. It might be easier to use this equation up here for some of them, or this one. For 0, this equation is easier, I would say. And you get 256. For 16, I would say this equation is easier because it's just 16 squared, which is also 256. For 8, I'd say this equation is easier. So 8 squared plus 8 squared, 64 and 64 makes 128. So this one just says minimize the sum of their squares, while the minimum is 128 by the extreme value theorem. So the minimum, that is not how you spell minimum. That's close to how you spell minimum. So the minimum is 128. If it asked for the x and y values, it would be 8 and 8. So these first two examples, we were able to find a closed interval and then apply the extreme value theorem directly. Not all examples are like that. So let's look at a few more examples. Let's see, a box with a square base and an open top is to be made with 1,200 square feet of material. Find the dimensions that maximize the volume of the box. So again, first thing I like to do, find a function we're doing calculus on. This question says find the dimensions which maximize the volume of the box. So we're going to be maximizing the volume of the box. Well, we need a volume function. Well, we need a box. Square base and an open top. So here's a box. It has a square base and an open top. Square base tells us that this side and that side are the same. But nothing else is necessarily square. Well, I guess the top is square. But the height of the box is not necessarily the same as x. So we have the square base, and we have a second variable for the other direction. So we're doing calculus on the volume, which is x squared y. Again, a function of two variables. So we'd like to eliminate one of those variables. Well, we can because we have other information. It tells us the box is to be made with 1,200 square feet of material. Well, that means the surface area is 1,200 square feet. What's the surface area of this box? So I'm going to write other words here. We're doing calculus on this function. This other equation is called a constraint. So you could phrase it as we have a function such that, given a relation between x and y, such that what is 1,200? Such that x squared plus 4xy is 1,200. Why is that? Well, if we look at all of the sides of this box, well, all the sides of the box put together make 1,200. The bottom of the box has area x squared. The top of the box doesn't exist. Open top. The four sides, each of the sides is an xy. So the 1,200 square feet of material covers the bottom and the four sides. The bottom is x squared, each side is an xy. So x squared plus 4xy equals 1,200. Well, we can use this to eliminate a variable. I'm going to solve this again for y. So I'll say, y equals, not 1,200 equals. So y equals, we'll solve it for y. What do you get? You get 1,200 minus x squared over 4x. I'm not going to simplify that. But we have now solved for y, so we can eliminate the y from our volume function. So the volume is x squared times 1,200 minus x squared over 4x. And I'm just going to distribute this. But before that, notice an x here is going to cancel with an x here. How many x's is that? That's 3 x's. So, how did I do this? Well, I canceled one x with this. Then I distribute the x through. 1,200 over 4 times x gives 300x. X squared over x. Well, the second one, I guess in simplifying, I didn't look at canceling this x with that first. I distributed the x and then split the fraction. Either way, this last one you get x to the fourth over 4x, so x cubed over 4 with a negative sign. Either way. Now, we've written this as a polynomial, so we can find the maximum. Now, in the first two, we were able to find a closed and bounded interval, which defined our x values. Here, that's not necessarily the case. The x values here, x can't be 0. You know, that wouldn't make sense here. You know, if x equaled 0, you'd get 0 equals 1,200. But x can be any number larger than 0. So the x values here are 0 to infinity, not a closed interval. So we can't apply the extreme value theorem. But we will do something else to conclude that this gives us a maximum. We do have other calculus we can use. Well, maybe I'll say it now. When we were doing graphing, a consequence of the mean value theorem, well, you could interpret it with you could interpret a maximum and a minimum using the first and second derivatives. You could say, for a maximum, it's going to be increasing and then decreasing. For a minimum, it'll be decreasing and then increasing. But instead, what I'm going to do is make a second derivative observation and observe that if the second derivative is always negative, a critical point will look like that because it's always concave down. If the second derivative is always positive, a critical point will look like that. It's always concave up. So let's do that. We still want to find the critical points. So v prime equals what? 300 minus 3/4 x squared. We want to set this equal to 0. This equals 0 when x squared equals 400. Because if this is 400, then you get 300 minus 300 equals 0. X can't be negative. So we have x equals 20. And I walked into a table. We have x equals 20. Well, find dimensions that maximize the volume of the box. We don't know right now that this gives a maximum. In the other ones, we were able to conclude it's a maximum using the extreme value theorem. But here, we need to make an observation. And I'm going to use the second derivative to make this observation. This gives a maximum since v prime prime. What is the second derivative here? Well, it's -3, since v prime prime equals -3 halves x. And -3 halves x is less than 0 when x equals 20. Now, why does that tell us it gives us a maximum? Well, the second derivative being negative around this point tells us the function is concave down. But in particular, it tells us that the critical point is going to be at the top of a mound like that. So that means x equals 20 will give us a maximum. So right here, this argument gives us a maximum. Then we go back and make sure we answered the question, and we didn't, because it says find the dimensions. This is just one dimension. So x equals 20, and y equals, what does y equal? Well, if x equals 20, what do you get? You get 400 plus 80y equals 1200. 80y equals 800. Y equals 10. So x equals 20 and y equals 10. So here we didn't apply the extreme value theorem because we couldn't find an interval on which we could apply the extreme value theorem. But we could use a second derivative argument. In these, you technically could do a first derivative argument as well, but they generally are more detailed because you need to do an increasing then decreasing. So I would stick toward the second derivative. Let's look at a couple more examples. Let's see. Let's do, yes, this one. A pizzeria. Pizzeria has an E there for some reason. Sells pizzas, which has an A, for $13 each. The cost to produce X pizzas is C of X equals what? 13 minus 11x plus 3x squared. Two parts. Find the revenue from selling X pizzas. Part B, how many pizzas must be sold to maximize profit? So we have a pizzeria sells pizzas, $13 each. The cost to produce X pizzas is C of X, that should be a capital C, equals 13 minus 11X plus 3X squared. Find the revenue from selling X pizzas. How many pizzas must be sold to maximize profit? So before doing anything with maximizing profit, we need a revenue function. Well, the revenue is how much money the pizzeria takes in from selling pizzas. Well, X pizzas, $13 per pizza. Do a unit conversion argument, $13 per pizza times pizza. Pizzas cancel, you're left with dollars. $13 per pizza. So 13x is our revenue function. Part B. How many pizzas must be sold to maximize profit? Well, profit, we'll assume they have only pizzas, because that's all we're given. Remember, profit, maybe I'll say P of X, is what the company, the pizzeria, takes in minus what they spend. So revenue minus cost. What's the revenue? 13x minus the cost, which is given. Subtract the entire cost function, simplify this, and what do you get? You get negative 3x squared positive 24x minus 13. Now, again, like in the last one, our domain of x values is the open interval. Well, technically it's the closed interval 0 to infinity. The extreme value theorem doesn't apply to that because it can't include an infinity. In the statement we have a to b. B can't go to infinity. It has to be a closed and bounded set. So here we can't apply the extreme value theorem, but we can do an argument like the previous one by finding the critical points and then interpreting them using the second derivative. So let's do that. What's our function? P prime. Could write P prime of x. Of x gets in the way a lot. P prime, negative 6x plus 24. We want to find where this is 0, where it's undefined, never undefined. The previous one also was never undefined. Equals 0 when x equals 4. So right here, this suggests that 4 is our correct answer, but we do have to interpret this. So x equals 4, the question says how many must be sold to maximize profit. It doesn't say what the maximum profit is. $35, I think. X equals 4 gives a maximum because of what? Because, well, we're going to do the same type of argument as before by taking the second derivative. P prime prime is negative 6. That's always negative. The function is always concave down. So the critical point will give us a maximum. And technically, in the last one I didn't draw this. You could throw this on a Cartesian plane and point out that 4 is there, and here's our profit function. You could, a little more detail if you want. But this does give a maximum because it's a critical point, and the function is always concave down. Let's look at 2 more examples. Let's do Could always do one of these two. Which one will I do? Let's do this one. I'll put the other one on the worksheet for a homework or something. Actually, no, let's do the other one. These first two we did were maximum. Well, what's the last one we're going to do? Yeah, let's do the minimum one here. Because the example after this is going to be a maximum. Of all rectangles with a given area, show the one with the smallest perimeter is a square. Well, again, we're going to need to find a function to do calculus on. It says what does it say? The one with the smallest perimeter is a square. So here we're trying to minimize perimeter. Let's take our rectangle. Of all rectangles with a given area. Well, here's a rectangle. The one with the smallest perimeter is a square. So I'll say doing calculus on the perimeter function, which is 2x plus 2y. That's two variables. Can we eliminate one? Well, we can, because it tells us of all rectangles with a given area. That tells us the area is constant. So I'll say such that x, y equals a. A is a constant. Maybe I'll specify that a little more. Such that x, y equals a, which is a constant. Now, this information does not give us a closed set on which, closed and bounded set on which our variables are defined. Because again, with this one, x and y can both be anything from 0 to infinity, not equal to 0. So we're going to need a second derivative argument eventually. But let's first get rid of a variable in our perimeter function. Let's get rid of y. So y, solve for y. Y equals a over x. So our perimeter function is 2x plus 2y, which is 2a over x. I guess I'll just write it like this. 2x plus 2a over x. And we're going to need the critical points, where it's 0, where it's undefined. P prime is 2 minus 2a over x squared. Derivative of 1 over x, negative 1 over x squared. 2 and a are constants. Where is this 0? Well, it equals 0 when what? I would normally write this as one fraction first, but I guess I didn't, so I'm not going to. Equals 0 when 2 equals 2a over x squared. Solve that for x, multiply by x squared, divide by 2, x squared equals a, x equals root a. Only the positive, because our possible x values are 0 to infinity open set. And this is undefined when x equals 0, but that doesn't happen here. That won't give us a rectangle if x equals 0. The constraint wouldn't make sense if x equals 0, I should say. The constraint wouldn't make sense if x equals 0. So it doesn't matter where x is undefined in this example. But we do have x equals root a. This, I'll say x equals root a. gives a minimum. We're trying to minimize perimeter. Since what? Well, second derivative is what? Or a over x cubed, which is positive. When, well, it's really positive when x is greater than 0 on our entire domain. So I'll just say that. You could say when x equals root a. I'll just say when x is in our domain. Where did that derivative come from? Well, negative 2a x to the negative 2. Power rule makes it positive 4a x to the negative 3. Now, why does this give a minimum? Well, this tells us the second derivative is positive. The function is always concave up, which tells us that our critical point that we found corresponds to a minimum. It's always concave up. And does this answer the question? Well, I don't think it clearly answers the question. We want to conclude the one with the smallest perimeter is a square. Why does this tell us it's a square? We've shown this gives the smallest perimeter. Why does this tell us it gives us a square? When is this a square? It's a square when x equals y. I don't see x equals y anywhere here. X equals root a, we need to show y equals root a. When x equals root a, y equals a over root a, which simplifies to root a. So it's a square. So definitely in these, be sure that you answer exactly the question that's being asked. You know, there are a few different concluding sentences. You could say, find the dimensions that do this. You could say, find the maximum volume or area or something. It could say, do that and then interpret it, as it did here. Let's look at one more example. This one I would say is significantly harder than the other examples we've done. You know, the others I would say fall under the category of easy or medium difficulty optimization problems. This last one I would say falls under the category of difficult but doable optimization problems. Let's see. A right circular cylinder is inscribed in a cone with height h and base radius r. Find the largest possible volume. Of the cylinder. Now, right circular cylinder just means it's exactly the cylinder, the soup can cylinder that you would expect. You know, circular just means the top and bottom are circles. Right means the rest of the cylinder is formed at a right angle from the base. But a right circular cylinder is inscribed in a cone with height h and base radius r. Find the largest possible volume of the cylinder. So we're going to do calculus on the volume of a cylinder. Which cylinder? Well, it's inscribed in a cone. Here's a cone. Let's see how this drawing is going to turn. It's inscribed in a cone. So it'll look something like this. I don't know if I want to draw the backs of these or not. I don't think I need to draw the backs of the bottom. The top will give us all we need. So we have our cone. and we have the cylinder inside it. So the cone, of course, it's circular, so this top circle of the cylinder does intersect exactly with the cone. What information do we have? The height of the cone is h. I'm going to label it on the side so that it's not in the picture, because we're going to need labeling inside the picture as well. The base radius is r. Base radius of the cylinder, not the cone, is r. Now, we need the volume of the cylinder. I'm going to work from up here. Right there is the center. The volume of the cylinder is defined by its height and its radius. But notice, well, the radius is given by that distance. Depending on where this cylinder is, if it's a tallish cylinder, that radius is going to be small. If it's a wideish cylinder, the radius is going to be large. But in particular, it's variable. I'm going to call it x. The height of the cylinder, I'm not going to draw the height like this. I'll explain why in a moment. It would make our next observation more difficult. I'm going to describe the height. We know the entire height of the cone is h. So that means the height of the cylinder is h minus whatever that distance is, which is variable. Let's call it y. So what is the volume of the cylinder? Volume, it's what? It's pi r squared times the height. So it's pi, the radius of the cylinder is x, so pi x squared, times the height, times h minus y. H, remember, is a constant. X and y are not. So we need to eliminate either x or y. How are we going to do that? Well, it may not be obvious with this drawing, unless you know exactly what you're looking for. But it may become a little more obvious if we take this h value and throw that line on the actual height. Because right there, we know that this distance is h. We know that this distance is y. This distance is r. This distance is x. If you slice this right down the middle, I'll say to eliminate either x or y. Slice that right down the middle, look at half of it. It gives us a couple of right triangles. In particular, it gives us two similar right triangles. By similar triangles, the ratio of the sides are going to be a constant. They're going to equal each other. So I'll say, why are they similar? Angle, angle, angle. Here's our small triangle. I'm going to take y over x equals the same ratio of the larger triangle, h over r. And right here, this gives us a relation between x and y. So I'll solve for y. So y equals h over r times x. And we can substitute that into our volume equation. I'll do that over here. Then volume equals pi x squared times h minus y. So h minus y, h minus h over r x. And now I'm just going to distribute this. I don't want to deal with the product rule. I'm also going to put constants out front. So distribute onto h pi hx squared minus pi h over r times x cubed. Now, I'm just going to look back over here and make sure I didn't make a mistake. I don't want to make a mistake now and notice it later. Pi x h, yeah, okay, that's right. So right here we have our volume function. And now we're going to maximize that. Now first notice the possible x values here. Again, not equal to. That was the entire point. That's not equal. The x values are defined on an open interval. And x can't equal 0 here and satisfy our constraint relation between x and y. And similarly, x can't equal r, because then it would be, what, an infinitely flat cylinder. So we're going to need, eventually, a second derivative. Right? You can't apply the extreme value theorem directly. But let's find the derivative, find where it's 0, find where it's undefined, and so on. V prime. Derivative, 2x minus 3 pi h over r. Pi h are all constants, times x squared. We want to set this equal to 0. Fine, it's never undefined. How are we going to set this equal to 0? I guess I'll factor it. I don't know. I guess I don't have to, but yeah, I'll factor it. Everything has a pi. Everything has an h. Everything has an x. Pull that off of this, you're left with a 2. Pull that off of this, you're left with a negative, a 3, an r in the denominator, and another x. It equals 0 when x equals 0, not in our domain, or when 2 minus 3 over r x equals 0. Solve that for x. 3 over r x equals 2. X equals 2r over 3. And find the largest possible volume of the cylinder. I claim that that gives us the largest possible volume of the cylinder. Why does this give us the largest possible volume of the cylinder? Well, I'll do that here. X equals 2r over 3 gives a maximum, since, well, for a maximum we're going to want to show that our volume function is concave down. Can we do that? Well, V prime prime is 2 pi h minus 6 pi h over r x. I want that function, so I don't want to erase it. And why does this tell us it's concave down at our relevant value? And we're evaluating this. Notice x is in here, so we need to evaluate it at our x value. So v prime prime of 2, not 2 pi, 2r over 3 equals 2 pi h minus 6 pi h over r, 2r over 3, substitute 2r over 3. What does it give us? Well, r and r cancel. 6 and 2 make 12. 12 over 3 gives us 4. Pi and h are still there, and the negative is still there. Equals negative 2 pi h, which is negative. Guess I'm erasing it. Which is negative, so that tells us our function is concave down near our relevant value, which tells us it gives a maximum. Now this doesn't answer the question, because we want the largest possible volume. We don't just want the x value. So I'll just answer that here. The largest volume is then what? Volume evaluated at 2r over 3. What's our volume function? Where's our volume function? Equals. You could use the distributed form. I'm not going to. Equals pi times 2r over 3 squared times h minus h over r, 2r over 3. Need to solve that. Well, simplify that. So it equals what? 4r squared pi over 9 times what? What is this? H minus 2/3 h, because the r's cancel. So this parentheses just simplifies to 1/3 h, which is why I used the factored form. And this equals 4 pi, I guess I should leave it in the same order, 4r squared, I like pi first, 4 pi r squared h over 27. H and r are constants. Now, so these optimization problems could get pretty involved, but I definitely wanted you to see a similar triangles argument. Similar triangles show up a couple times in calculus. They also could show up in a related rates application, but I like this question more than the related rates one, so I chose the optimization application instead.